Hello, everybody. I want to talk about two very important theorems in calculus that you're going to utilize a lot as you go to beyond this class. They are the extreme value theorem, often called the EVT, as well as the mean value theorem, also called the MVT. Okay, so we're going to talk about these, what they tell us. We're going to, talk about them in a very strict mathematical sense, but also in a more general sense, what it tells us about these pieces. So, starting with the EVT, given a function f of x that is continuous on the closed interval AB, the absolute max or minimum occurs at either A, B, or C, where C is a critical point. Essentially, what the extreme value theorem does and tells us is your absolute maximum or minimum will either occur at what is sometimes referred to as the endpoints or at a critical point. And you definitely only have to check a finite number of them. It turns an infinite search into a finite search. That's literally saving you an infinite amount of time. So let's take a look at an example. Let's say the function f of x is e to the x, and let's say the interval is 0 to 3. So we're going to make a table to check. So here are x's, and here are f of x's. What do we need to check? We need to check 0, because it's an endpoint. We need to check 3, because it's an endpoint. But we also need to check, maybe, the critical points. So if we set f prime of x, which is also e to the x, to 0, what do we get? No solution. Therefore, we don't have any critical points. We only need to check f of 0 and f of 3. So plugging in f of 0, we get 1. And plugging in f of 3, this will be e to the 3, which is approximately 20.086. So I can tell you with absolute certainty, this is the absolute minimum on this interval, and this is the absolute maximum. Somewhat of an easy, or shouldn't say easy, but maybe a simple problem, but maybe we can get something a little more interesting. Let's do a very similar looking problem. Let's go x squared times e to the x. So, what are we going to have to check? We're going to check 0, and we're going to check 3, but we also need to check some critical numbers. Okay. So we find the derivative using the product rule. We set it equal to 0. It's going to be e to the x times x squared plus 2x equals 0. Or e to the x times x plus 2 equals 0. We're going to find x equals 0 or x equals negative 2 are critical points. So actually, in order to find this one, let's do this one for negative 3 to 3. Just because I want to include all of the critical points. So why do we check negative 3 and 3? We check them because they're endpoints coming from our interval. But what else are we going to check? We're going to check are critical points, 0 and -2. These are critical points. Once again, we're going to plug these in. So we have e to the 3, which again is approximately 20.09. Oh, sorry. This should be e to the -3. We're going to get 0.0498. We're going to get 20.0855. We're also going to get 1, and we're going to go second e to the power -2. We're going to get 0.135 ... So, where are the absolute min and the absolute maximum? Well, this is a finite list. We just look for the smallest and the largest. The smallest is the absolute minimum, and the largest is the absolute maximum. Turns out the critical points in this specific case didn't really change that much from our calculation. Okay, so maybe we want to take a look at a graphical reason why this is true. And this is not by no means a proof. But if you think about it, let's say we have some function and it has some relative mins or relative maximums. And let's just say we arbitrarily cut off window right here. So this is what we care about. This is what we see. This is where we are. So where could the minimums and the maximums be? They could be at the critical points, but they could also be where we cut them off. Right? Notice this point is a little bit higher than this point. And so what we're essentially saying is you check the beginning of the interval and the end of the interval and all the critical points in between. And in that finite list, you are guaranteed an absolute minimum and an absolute maximum. That is what the extreme value theorem does. Okay, let's go over here and let's talk about the mean value theorem. Okay, very similar, given a continuous f of x on an interval, we'll say from a to b, we can say that the average rate of change is achieved at a point C between A and B. Okay, so I think this is one that we definitely want to take a look at the graph. And we're going to take a look at this, just this section right here. So notice, if I connect this point with this point, I'll get a line, and we can say that m of this blue line is f of b minus f of a all over b minus a, average rate of change. This is a secant. The mean value theorem guarantees that whatever average rate of change you achieve over the course of your interval, there's some point, which I'll call C, where M10 is f prime of C, and that these two values are equal. To put it in layman's terms, there is always a point C where f prime of C equals f of b minus f of a over b minus a. This is instantaneous rate of change, and this is average rate of change. There is at least one point where this is true. There could be more points, but it will always be true as long as you have a continuous function f and a well-defined interval a to b. If you don't have the interval, that's not necessarily true. But as long as you can define me a function and an interval, we know it. So let's take a look at a concrete example. We're going to start off pretty easy. We'll go e to the x times x squared. And we'll once again do the interval -3 to 3. You know, let's maybe not start with that one. Let's do a one that seems a little bit more obvious so you can get it. Let's just do a good old x squared from 0 to 2. Okay, so keep in mind this graph goes from 0, 0, 1, 2, 1, 2, 3, 4. Here's the point 2, comma 4. Go up like that. Okay, so step 1, let's find the average rate of change. This is going to be 4 minus 0 divided by 2 minus 0, which is 2, which is, of course, the slope of our secant line. Now, if we find f prime of x is 2x, and we set it equal to the insecant, 2x equals 2, we see it's achieved right at x equals 1. So if we connect that line, we should be able to sort of create that tangent line that mimics it. This is what we call the mean value theorem. Now, keep in mind, it does require you be continuous. It does require this interval, but as long as you have that, you should be able to solve for it. So let's do maybe a slightly harder one. This one is coming directly from your homework. We're going to do f of x equals e to the x on the interval 0 to the natural log of 21. That's our, and remember, this is an x interval. So, question 1, is f of x continuous on the interval? If the answer is yes, the mean value theorem applies. So, step 1, we're going to find the a rock, which is going to be f of the natural log of 21 minus f of 0 divided by ln 21 minus 0. Okay? So, plugging in e to the natural log of 21, we cancel, minus e to the 0, all over the natural log of 21 minus 0, which, if we simplify some things, we'll get 21 over the natural log of 21. That is our average rate of change. That means if we take the derivative, f prime of x, which just so happens to also be equal x, and we set it equal to that tangent line, the secant line slope, we can say e to the x equals 21 over the natural log of 21. Oh, I apologize. That actually turns out to be 1. It actually comes out to be 20 over the natural log of 21. My apologies. E to the 0 is not 0. E to the 0 is 1. So we want to solve this for x. We'll take the natural log of both sides. Be very careful with your natural log definitions, but we get x is the natural log of the fraction 20 divided by the natural log of 21. That is the point where the average rate of change is the instantaneous rate of change. And again, I think a lot of these proofs, and I'm not necessarily saying that this is a proof of it. I'm just trying to justify visually what's going on. So remember, we had 2 points, 0, 1, which we'll label. We also had the point. The natural log of 21. 21. We also had e to the power x. So, zooming in, we have this red dot and this blue dot that exists on this green line, e to the x. We can find the slope between them. We'll go y equals, the average rate of change was 20 divided by the natural log of 21 times x. We'll add plus 1. So notice the purple line travels through both points. It's the average rate of change. And the question is there a function on the graph, on the green graph? Is there a point where the tangent line at that point perfectly matches the slope? And the answer is yes. If we do y equals 20, the natural log of 21 times x, I'm going to do a minus c, because as we move it down, you can kind of see that eventually this green line and the black line, we're creating a tangent line at the green function. A rock equaling I rock. And that's the point of the mean value theorem, is that it tells us. Now, could there be more than one? The answer is absolutely. But for most of our intervals, as long as they're properly set, you're only going to find one. I will say, on question number, and I'll just shout this out, question number 8, I believe there are 2 points, but they have a certain parity. When you go to solve it, you're going to get a square root thing. So hopefully that helps you with that. So 2 important theorems, the extreme value theorem and the mean value theorem. And again, they all rely on this understanding of derivatives. Understanding that a derivative is a very precise mathematical object of a limit, but it also can be used in some very interesting ways. As always, if you have any questions, please let me know. I'll see you all in the next video.